Hi, is the mic working? Yep. So hi, my name's Pat. I'm really excited to be here. It's actually not the first time I've been to Budapest. I was actually living here. I lived here for about a year, about 20 years ago, so giving away how old I am. But I had a great time. Actually, I learned a lot of Hungarian at the time, and then of course, I forgot all of it. If you don't speak a language every day, you forget. So all I can remember is Nem beszélek magyarul, which I think means I don't speak Hungarian. So I want to talk about garbage collection today, and since it's the Ruby Python conference, I thought it would be fun to look at how garbage collection works in Ruby and in Python and compare them one against the other. So, because the two languages are so similar, I thought, well, probably the garbage collectors are similar too. So just a disclaimer, I'm a Ruby developer. I know nothing about Python except a little bit about its garbage collector, but we've got some smart people in the room here who do Python, so you shout out if I say something wrong and correct me. So before we get into the technical stuff, why talk about garbage collection in the first place? Like, it doesn't sound like in the real world, being a garbage collector is certainly not really a good job to have. Even in computer science, it doesn't seem really glamorous or exciting. Like, how many people here are excited by garbage collection? Wow, actually, a few of you are. That's pretty cool. Well, I'm excited by it too. But you know, most of the time, it doesn't seem very exciting. And you know, it's like, actually there was a blog post in the Ruby community in the last month or two where someone said, if you change your garbage collection settings, then your code will run, your unit test suite will run 20% faster. So that sounded kind of cool, and it's good. Running code faster is good, and you know, having fewer pauses is good, but it's not really exciting. It doesn't get people excited. It's not really interesting. But I think that's completely wrong. I think garbage collection actually is exciting, and one of the reasons why is that it gives us a chance to look at some of the more interesting algorithms in computer science. So as we'll see in a minute, the algorithms behind Python and Ruby's garbage collectors are over 50 years old. And not only that, there's new research going on too. You know, so there's something called Rubinius. That's a version, one of the implementations of Ruby. Rubinius's garbage collector was invented, the algorithm was invented in 2008. So there's very old stuff and very new stuff, and it's actually one of the more fascinating topics in computer science. So another reason why is that, you know, I like to think of this expression, you can learn a lot about someone from their trash. You know, if you go outside of someone's house, or like archaeologists and anthropologists, if they go back and they study some ancient, some ruins or some ancient civilization, the kind of things that they're finding in the ground are what people left behind, what they threw out, their garbage. So you can learn a lot about a culture or a city from its garbage, and I think if you want to learn about how programming languages work, if you look at the garbage or how they handle garbage, you can actually learn a lot that way too. But the other thing though is that the name garbage collection is kind of a misnomer. Garbage collectors do much more than simply collect garbage. So they actually do three things. So the first thing they do, which is kind of counterintuitive, is they first allocate memory for new objects. So when you create an object, you create some sort of structure, you actually are interacting with the garbage collector. And that sounds weird, but it's true. And then identify. Garbage collectors have to identify what your which objects are garbage. And that's sort of obviously what we expect garbage collectors to do. And then finally, they have to reclaim. So once they've identified all those garbage objects, they have to reclaim or recycle the memory from them so you can create more new objects. So I'd like to think of another analogy to describe this. You know, if your application was the human body, this is not Hungarian. This is, anyone know what language this is? Polish. All right. So, and these are not, I don't think they're talking about garbage collection. But if you, you know, all the code that we write in Ruby and Python is usually business logic, right? So it's, you know, all the elegant algorithms and all the beautiful code that we write. I like to think of that as the brain, right? That's the intelligence of our application. And it's what we're thinking about, what we're doing. It's what our body is really there for. So what part of the body do you think the garbage collector is? Well, it's not, no, so I actually disagree. It's not the part of the body related to collecting garbage and bodily waste. I think it's actually your heart. I think the garbage collector is like the beating heart inside your application. Why? Because it provides memory, it provides new objects, you know, blood and nutrients that flow through your whole body, your whole application. You know, if your heart stopped beating today, you would be dead immediately. If you had high blood pressure or you had clogged arteries or you know, if your garbage collector started to slow down, your application is going to slow down and eventually die. If your garbage collector stopped working, your application would be dead immediately. So anyway, so the point is garbage collection is actually very important. Not only is it fascinating, it's important. So here's a little example. I'm not going to have much code today. It's going to be really high-level conceptual discussion, but a little bit of code just to give us something to talk about. And I won't even explain this, but it's one thing that's fascinating. Again, I'm a Ruby developer, but the more I learn about Python, the more I realize it really is the same language almost. It's like two different ways of saying the same thing. It's really striking. I never knew much about Python. You know, init or initialize or self.value, add value. It's all really the same thing. So I'm going to use this node class as an example today, and we'll be passing, just passing in values when we create nodes, just to, be able to keep track of which node is which. So let's start with, so down here, when I say node.new or node in Python, how do I get a new object? What happens inside the language when I create a new object? So how do garbage collectors allocate new objects? So they actually use an algorithm called the Freelist, and this is one of the oldest computer science algorithms out there. This was invented by a guy named John McCarthy. Many of you probably have, maybe not have seen this picture, but he's a giant of computer science. He invented Lisp back in the late 1950s and early 1960s. He worked at MIT, not far from where I live in Boston. And one of the amazing things about Lisp is not only was it one of the first functional languages and still being used today, 50, 60 years later, but all the other things that he invented along with Lisp, as part of its implementation. And garbage collection is one of those things. So the original version of Lisp from 1960 had a garbage collector, and it used the Freelist algorithm that we're about to see. You can go and read John McCarthy's academic paper on this. So it's called Recursive Functions of Symbolic Expressions and Their Computation by Machine, Part 1. So I thought that was kind of funny, because there's no Part 2. Part 1 was enough. He got it all in Part 1. And it goes, we're not going to read this today, but it goes into detail about, what are lists, and Lisp means list processor, and all the stuff about, so symbolic expressions and all that stuff. But one of the things he talks about is what he calls the free garbage list, I think, or free storage list. So it's more generally known as the free list. And just to give you an idea of how long ago this is the first computer that ran Lisp. This is called the IBM 704. And this was built in 1963. That's even before I was born, so this is a long time ago. I'm sure all the phones and laptops in this room have thousands or millions of times more memory and computing power than this computer had, which is, the computer is like the whole cabinet over here. But this ran Lisp, and it ran the garbage collection, and it ran the same algorithm that we're going to see today. And this, it actually reminded me of something that Stu Holloway said yesterday about how a lot of the algorithms that do mutation, the stuff that he was explaining, was a bad idea. We did them, and we do them because we didn't have much memory at the time. It just got me thinking about, how much memory does this actually have? I haven't had time to look it up, but it's probably not, 3, 4 gigabytes of RAM. So anyway, so let's get to the free list. What is a free list? So if we start with Ruby, one of the things that surprised me about Ruby when I started to study how it works internally is that when you create an object, nothing really happens. In fact, when you run a Ruby program, before your program ever runs, before any line of code in your code actually executes, Ruby has already created many new objects. In fact, it creates about 10,000 new objects. So each one of these squares in my diagrams, and so I like to use a lot of diagrams and explain things visually with boxes and arrows. So this is all very simplified. I mean, in reality, when you run a Ruby program, it creates about 10,000 of these things, and there's actually a bunch of different lists, but whatever. Conceptually, it's one list of objects. So each of these is a structure. It's called an R-value structure, and it just holds one object or value inside of it. And this is a linked list, so there's a list of these that are in memory. And so if I go create an object, if I say, for example, node.new, and I, put an ABC. So this is the ABC node over here. This just helps us see which is which. And I say I have a reference or a pointer to it in N1. Ruby doesn't have to do anything. All it does is says, oh, here you go. So it takes it off the list and gives it to me. And all these other ones are just sitting there waiting. So it's very fast and actually efficient. But this whole idea was, again, invented 53 years ago or whatever. So this is nothing new. And I don't know if that's good or bad. If Ruby uses the same algorithm that Lisp did 53 years ago, not necessarily a good idea. But the basic idea is the same. So as I create more objects, it just takes more of these things off the list. And the list gets smaller and smaller. So what about Python? How does that work? So here, things work a little differently. Python, it turns out, does use a free list internally, but not globally in the same way that Ruby does. It uses it to recycle some types of objects. So in Python, when I create a new object like this, node of ABC, or DEF or whatever, GHI. It's just allocating memory for those particular objects at that time, and then we have 3 pointers like this. So that's how allocation works, and they're a little bit different, but still Python and Ruby seem kind of not too different one from the other. So what about the next thing, identifying garbage objects? So, but before we get into that, what are garbage objects? It seems obvious, but maybe that's not that obvious. Why don't we talk about that? So in Ruby, suppose I continue to create some more nodes. I say, N1 is new node new JKL, node new MNO, etc. So as I create more objects, it does the same thing. It just gives me more of these pre-created structures, just hands them off to me from the list. But what it does, though, is it leaves these other ones behind. Like, these don't go away. They just sort of sit there and remain in memory. So the way I like to think of this is, if you're a Ruby developer, it's like living in a really dirty household where no one cleans up after themselves. Where you've like got, dirty clothes all over the floor and blah, blah, blah. You can imagine, you see what I'm getting at here. So we get used to living in a sort of dirty garbage environment because everything that we do is just sort of lies around and doesn't get cleaned up. Python, however, so here we're getting to sort of the philosophies of the 2 different languages, and they're a little bit different. Python, however, uses this algorithm here, reference counting, and this is different. Python is like living in a really clean house where people are really well organized, and as soon as they're cleaning up and sweeping all the time. And the reason why is this algorithm. So this was invented not coincidentally in the same year. Michael Bernstein, a friend of mine from New York, in his talk about garbage collection said, he had a great line, 1960 was a great year for garbage collectors. So John McCarthy did the Freelist, and this guy, George Collins, not far away in New York, invented this other algorithm called reference counting. So we won't read this either, but I just think it's fun to look at these old papers and read them. So what is reference counting? How does that work? And so a lot of the Python people in the room might know all about this, but every time I create one of these objects, so we had this example, ABC, DEF, GHI, what Python does, it saves a number inside each object. So this is the reference count, and that just is a count of how many different pointers or references point to that object. So they all start out at 1 because initially there's only 1. So the way it works, though, is if I create another one, if I now say N1 is node of JKL, it gets a 1 too. Great. But the important detail here is this one. So N1 used to point over here. This is now set to 0. So when a pointer changes from one thing to another, in Python, not in Ruby, it decrements that reference count. In a similar way, and what happens is the garbage collector, the Python garbage collector, comes alive immediately, comes in here and cleans up that object. It knows right away. If you hit 0 on the reference count, I don't need that anymore. It's time to get rid of it. So that's why it's like living in a really clean house. As soon as you make a mess, Python comes along and cleans it up. And the nice thing about that is garbage collection in Python happens continuously over time. They're not these big pauses or gaps, as we'll see in a minute with Ruby. So another example is if I take N2, I say N2 is N1. Now this one gets incremented up to 2 because there are 2 pointers pointing to that object. This other one over here, now this was 0, so it gets cleaned up and it's gone. So what about Ruby? Ruby works a little differently, as you might guess. So eventually, the problem with the free list is eventually it runs out because we're not cleaning up any of these other objects as we go. They're just sort of lying around in memory. So what happens in Ruby is when the free list runs out and there are no more objects to give to my application, Ruby has to run a garbage collection. So how does that work? It uses something called mark and sweep. So let's go through the basics of this, and then we'll get to some more advanced stuff in a little bit. So the way mark and sweep works is first, Ruby actually stops your code. So unlike Python, which ran continuously as you change pointers, it cleaned up after you, Ruby has to stop the whole application for a fairly long time. So it's like stop the world garbage collection. And what it does is it marks all the objects. So this is where the mark part comes in. It says, okay, N2 is here, N3 is here, N1 is over here. So for these objects, I'm going to mark them. I'm going to put little, in my diagram, I use M for mark. In reality, Ruby, at least Ruby 2.0 and later, uses something called bitmap marking. Okay, so this just means instead of M's, what really happens is it saves 1s and 0s in this thing called a free map or a free bitmap. And if any of you are familiar with Unix copy on write optimization, so I won't explain this carefully, but if you have 2 processes that have the same values in memory, Unix can actually share those memory pages. So the reason for this is that if you put all these bits somewhere else, not inside the objects like the reference counts we saw with Python, it can actually allow the Unix memory optimization to work a little better. So Ruby's ahead of Python just in that one way, at least. But anyway, that's a detail. What happens actually is, now that we've marked some of these as active or live objects, like we know that my code is still using these ones, it means these other ones I'm not using, so they're garbage. So these are garbage objects, so that we've identified by walking all the different pointers in my application. And actually I'm not showing that today, but that's a hierarchical, complicated thing called an object graph. So by doing that, I'm indirectly identifying the garbage objects, and then the sweep part happens, which is, okay, now that we know these are garbage, let's just put them back on what? On the free list. So they go down on the free list, and now I have a bunch of new objects that I can recycle and give back to the application. So your objects actually, they don't just get thrown out. They like relive another, they're reincarnated into a new life. You know, so when you're done with a certain string, it might become an array in a few milliseconds or microseconds. There's something else called lazy sweeping, which is just that instead of sweeping all the garbage, we only sweep a few of them up, just enough to keep the application running. So that's a way of reducing the time that this takes. Because remember, while this is going on, your code is not running. Your code is stopped. So this is a big problem in Ruby. Another interesting detail about Python is that you know, if we create an array in Python, and help me out, I think arrays are called lists for some reason. So if we create a list in Python and we put a few things in it, you know, so there's a hierarchy of pointers. One of the things about this reference counting that's not obvious is if you say list is none, I think none means no, it'll set this to 0, but then it has to also recursively figure out everything that was in the list has to be set to 0 too. So be careful in Python. I don't know if you guys think about this a lot, but when you delete something or stop pointing at it, that process of freeing stuff can be recursive. It can actually go through thousands of objects all at once. So there could be pauses in Python as well. Okay, so let's look at one of the more complicated problems with reference counting. So, you know, going back to 1960, right away, this is sort of a big problem with the algorithm, which is it doesn't always work. And so what do I mean by that, and what are cyclical data structures? So in Python, let's suppose, same example, I have two nodes, A, B, C, D, E, F, okay, pretty simple. Now let's say I want to create a doubly linked list. Let's say I want to have each node use a next pointer to go to the next one, and the other one goes back to the previous one. So I want to say, you know, node 1 next is node 2, and node 2 previous is node 1. So pretty good. So notice that the reference counts went up to 2. So they went from 1 to 2. Okay, makes sense, not a big deal. But now suppose I say n1 is none, and n2 is none. So I stop using the linked list. Well, what I want to have happen is I want that list to go away. I want all those objects to be released because I'm not using them anymore. So why do I need them? But the problem is their reference counts remain at 1 because they're actually referring to each other. So this is a really simplistic example, but this could happen a lot in Python. And what actually happens is that, yes, most of the time Python cleans up after you, but sometimes it can, you know, garbage begins to collect in memory over time. And so Python actually still has some amount of garbage. You know, its house is still a little bit messy. So what does Python do about this? So another interesting detail of the Python garbage collector is it has a linked list, sort of just like Ruby, but it's not a free list, it's a live list, so to speak. It's actually called generation 0 linked list. So every time you create an object, it puts it on a linked list. So if I create another one, it puts it on that too. And what Python does after a while, it has this, it takes a measurement. It counts how many new objects you create and how many of them are freed. And if too many more are created than freed, if that difference gets bigger than a certain amount, Python will actually stop and say, okay, we need to go in here to this list and figure out if there are any cycles or cyclical data structures. And so the way it does that, it uses a really interesting algorithm. It goes through the list and it figures out how many of these things were pointing to other things in the same list. How many, you know, cycles were there. And it figures out which of those were, and it decrements those counts down to 0. While at the same time, some of these other objects might still have references from elsewhere in the application. So in this way, now we know, okay, this one and that one and that one, these actually are part of a cycle, so we can get rid of those. So this is how Python periodically cleans up these extra structures. And then we'll get into this in a minute, but what happens after that is it moves these remaining ones into something called generation 1. So Python also uses something called generational garbage collection. It has 3 generations. It has generation 0, 1, and I guess generation 2 is what they're called. And so let's get into that. What is generational garbage collection? Why would I want to do that? So this all depends on something called the weak generational hypothesis. I don't know if any of you have any of you ever heard of this before? Okay, so the basic idea is very simple, which is when I create a new object, whether, you know, Ruby, Python, or any language. So here I'm saying node new. The idea is that most of the time, when I create objects, they have a very short lifetime. So usually if I create something like this, I use it within one method and I'm done with it. Or maybe I return it from a method and I use it in another method and then I'm done with it. If I have a Ruby on Rails application, for example, during a single request, I probably create and then I create and use thousands of different Ruby objects. But as soon as that request is over, I'm done. Those are all garbage. So the idea is that for most applications, most of the time, new objects quickly become garbage. And only a few objects, like for example, a session variable or a controller or something like that, would remain active for a longer period of time. And so those other objects, once they live a certain time, they're more likely to live on and continue. So, so Python does this. We saw it just a minute ago. So now Ruby, Ruby's a little bit behind the times with garbage collection, to say the least. But finally, in Ruby 2.1, which just came out, a preview version just came out a few weeks ago, we're starting to use this generational GC idea. And Koichi Sasada from the core team has been working on this, I think, for at least a year. So I'm going to just touch on the basic idea behind it, and there's a lot of complicated implementation details which I'm going to avoid. So let's go back to our Ruby example. So as our, let's say our garbage collection is about to happen, and we've filled up, we've created all these objects, and we have a few live ones and some other garbage ones, but the free list is empty. And so the system stops, and it's time to do garbage collection. So what Ruby 2.1 will now do for the first time, and by the way, Rubinius and JRuby, of course, have been doing this for years. So I'm just talking about the standard MRI Ruby. And the JVM has, 3, 4, 5, 6 different possible algorithms and different ways of doing this. The JVM is very sophisticated, but the same basic idea applies, which is that you divide your objects into these two what are called generations or collections. So there are young objects that are likely to die quickly, and then if an object lives past a certain time, we move it over here as a mature object. So let's suppose, my list, let's say there are 3 live ones and some other garbage ones. So what happens in Ruby 2.1 is that if an object lives long enough for me to mark it, if I create it and it's still live, it's still being used by my app, the next time a garbage collection runs, we move it over to the right. So in Ruby, there's just one generation, one collection or generation. In the JVM and Rubinius, there's different numbers of these collections. I think Rubinius has 2, and the JVM has maybe 3. So the Ruby 2.1 algorithm is actually pretty simple. So you move these objects over here. Now they're mature objects. So what this means is I'm not going to mark them again. So I've marked them once. They're still active. They're still live. So I'm deciding. Ruby thinks that, okay, they're still active. They're probably one of these objects like a session variable that's going to live on for a long time. So I'm going to just assume that it remains active and alive. Whereas these other things, these are garbage, so I'll clean them up. Then the application continues, and these just stay over here, and I assume they stay alive, so I don't check them. But the next time we have to do a garbage collection, we only run the mark and sweep on the young objects. So here, all these are new objects I've created since, and now I've marked a few of them as live, and there's some more garbage ones. So the basic idea is that since most of the new objects are young, and they die quickly, most of the garbage is going to be over here. Some of these ones might have become garbage in the meantime too, but that's not as likely, according to the hypothesis. So Ruby will not do mark and sweep on the mature objects. They'll just live on, not forever, but they'll live on longer, and it only will do the mark and sweep over here. So it will do a full collection after a while if the mark and sweep on the young objects is not enough to get me enough new memory. So if I continue to run out of memory, it'll actually do a full collection. So this works really well, and it reduces the amount of time that we spend doing GC, and we're doing our GC just on the things that really need it. So it's a big step forward. And I think Ruby 2.1 is a big advance in that, at least for garbage collection. But just like the cyclical data structures, there's a big problem with this algorithm too, which is if we're not doing mark and sweep over here, if we're not looking at these objects, what happens if I create a new object and I put it here and I'm adding it to an array? So these arrows mean each of these objects are referring to other objects. So like this could be an array or a hash that has something in it, just like that could be an array or hash. So what if I modify a mature object and I say, I'm adding something to this array? The problem is if I'm not doing mark and sweep over here, right, the mark algorithm is not going to find this. It's going to mark these ones over here, but it's going to think this is garbage because it's never going to get marked. So what will happen is Ruby will suddenly free this. It'll delete it. So that would really suck. If you created stuff, put it in an array, and then Ruby just deleted your value. That wouldn't be very nice. So the big complication with the algorithm is Ruby and every language, if they use this idea, the JVM does the same thing, Rubinius, is that they need to monitor all these mature objects to realize when I do this. When do I add something or add a reference to an older object, creating a new younger one? And so what you do is they actually use, I'm not going to get into the details, but they use something called a write barrier. So what the big change in the code for Ruby 2.1 is they had to add these write barriers to things like arrays and hashes and all the important classes in the Ruby code to detect when this happens. And when it happens, it puts this object on another little list somewhere, and it says, okay, this has to be another source of iteration for the marking. So it'll actually mark from here, and it'll mark from here, and so it'll find this one. So those are called write barriers, and that's basically how all this works. The big problem with MRI, by the way, is that because we also have these things called C extensions, which that's been a sort of headache for years for Ruby. Other C code that's out there running doesn't have these write barriers in it. So Koichi Sasada had to do a lot of work to figure out, okay, if an object actually came from a C extension, then what do we do then because it doesn't have a write barrier? So he has this whole other concept of, it's called shady objects, he calls it. So if you want to get into the details, the real fine level details, go check out Koichi Sasada's KO1's. He did a great presentation at Yoruko about 2 months ago, and it's like a 100-page PDF. It's got all the details on this. So that's it for me today. I don't have any more time. What have we learned? Python and Ruby are actually very similar, and I'm learning more about Python these days, putting this presentation together, and I want to continue to learn about Python. As the more I learn, the more it seems that they're really almost the same language. They're like just two dialects of the same thing. But internally, they work very differently. And I think it's important that we all learn how languages work, right? Because our programming language is our tool, and if you don't know how your tool works, you're not really going to be a very good programmer. It's important to understand the details, the stuff that James was talking about earlier this morning, and this sort of thing. I think it's important to understand the details, at least at some level, as you use the language to be a good developer. I just finished a book called Ruby Under a Microscope. It just went to print this week. So if you're interested in learning more about Ruby, how Ruby works internally, check this out. It's coming out as a real paper book by the end of the month, probably. Nothing in here about Python, so I apologize. So that's it. Any questions? You're all thrilled by garbage collection. You want to go and do garbage collection. Yep. Yeah, so concurrency. It's actually a similar problem to this. So the answer is yes and no. In MRI, in the new Ruby 2.1, it's going to do the sweeping part concurrently, but not the marking part. So the marking will continue to stop your application while it marks. If you want to speed up things by using multiple cores and have a real multi-thread app, the best way to do that is to use JRuby or Rubinius. And those algorithms do concurrent marking using the same write barrier idea. Okay, so they're able to mark at the same time as your application is running in another thread. But it's solving a similar problem because you can, if you've marked something, you can add a new object to something that you've already marked. So it's a similar write barrier solution. But that's not going to go into Ruby 2.1, maybe Ruby 2.2. I'm joking, I have no idea. Yep.
You said that Ruby allocates a lot of objects in advance.
Yeah.
When you run your script or whatever.
Yeah, when it starts up. Yep.
Does that mean that for really simple scripts, Ruby has a large memory footprint?
Not large, no. So it creates 10,000 objects. Each one is, it's in the book I read. I can't remember the number, but it's not a huge amount of memory, no. I can look it up afterwards if you want to know. So what Ruby will do, though, if you continue to, I'm sorry, maybe people didn't hear the question. The question was, when Ruby starts up, it creates all these new objects. How much memory does it allocate initially? What was I going to say? Oh yeah, so if you create more and more new objects and you never stop using them, if you create an array and you just put in thousands and thousands of things in the array will hold a reference to everything and nothing will ever get freed because your code is still using it. So Ruby will allocate more memory from the operating system. So if you just use more and more memory, it'll just get more and more memory. So the real answer is, write code that doesn't use a lot of memory. That's speed things up. Yep. To create weak references?
Actually, there is an API in the Ruby core, something like that. But for reference count, if you're in Python, I still see how that works. But how does that affect the mark and shift algorithm?
I don't know. No idea. Yeah. So the question was, what are weak references and how do they affect the algorithm? And does anyone know that?
I'm trying to answer. So weak references are basically, it's a reference, but it doesn't actually, like the object is not necessarily live. So if you drop down to one reference left, and so the only reference is the weak reference,
But then, I mean,
you can still throw the object away even though one person is holding on to it. And so I don't know much about how it's implemented in Ruby, but with reference counting, basically the way that works is when you're traversing, you don't mark. Actually, I guess I do know how it works in Ruby. When you're traversing, you don't mark something where you basically store weak references in a slightly different place than you would store regular references, and then you don't mark for those.
Yeah.
But it didn't really work properly in Ruby prior to 2.0.
Cool. Any other questions? Yes.
Last one.
What tools do so the question is, what tools do I use to figure out how things work? I'm an old-fashioned old person, and so I just like to put print statements in the C code. So I don't like to use, no, I find it actually easier to, if you want to figure out how Ruby works, and this would be my advice, you can use GDB, you can use a lot of sophisticated tools, but the best way is just to read the code and try to understand it, and put in print statements and recompile it so that you can get a sense of what happens, but more importantly, what happens in what order. And it's actually not that hard to figure it out. The C code in Ruby and in Python, I think, is fairly old code. It's a little idiomatic, it's a little unusual, but it's not that sophisticated. It's pretty simple.
Okay.
All right, thanks a lot.